Good morning. We are going to have today Daniela Stauber. She's from Córdoba. She's a graduate student and she's working with Gridap on elliptic problems. So she can tell us about all the secrets of Gridap and how to make meshes, etc. So I'll pass to her now.
Hi everyone. Leko, should I share my screen now, or maybe
Yes,
we will
you can start.
All right. Do you can see?
Yeah.
So, well, sorry for my English. It's been a while since I spoke English, so sorry about that. My name is Daniela Stauber. I'm a PhD student in physics under the direction of Oscar Reula. Thank you for inviting me, Oscar, Pablo, and Joaquin. In my PhD, we are working on finding numerical solution of stationary Einstein equations. Since we are working with elliptic equations, we choose final elements method for simulations, and within the zoo of libraries for this, we chose Gridap. So I've been fighting with the library quite been since 12 200 12 2021, sorry. Now I would like to tell you about some finite element applications. Two of three are relativity orientated. I know that this isn't a relativity course, so I would like to focus only in the PhD portion. Any question, please ask and stop me in every moment that you want. The first example is about initial data for general relativity. The main goal is to generate initial data in the conformally flat case without sources and with axial symmetry. Initial data in general relativity are these quadrupoles, where this is a 3D manifold. It's like a photograph of the spacetime. G is the Riemannian metric. It's a true tensor, a symmetric true tensor. The extrinsic curvature and the sources. And this quadrupole satisfies the following constraint equations. And with a conformal mapping, this is important now. But with this conformal mapping and this decomposition of the extrinsic curvature, we can rewrite these equations in this way. This is the main goal for now, where C has the information of the metric, and the other scalar field F has the information of the extrinsic curvature in the A vector. So for now, this is the equation that we'd like to work. We have to note that this is a nonlinear PDA, and in this case, the equation has a weak couple. Note that we can solve first the equation of for f, and after that, having the solution of f for f, we can use it to find the solution to C. The boundary, this is an elliptic PDA, so we can use a final element to solve it. We will do it with Gridap. The domain for this equation are this one. The domain is we have axial symmetry, so we can use cylindric coordinates because of the symmetric symmetry. The equation are 3D, but we can solve it only for these two coordinates. And the boundary conditions that we would like to impose are this one, Dirichlet for the origin, and oh, the uh, the K-main for the infinite boundary, we would like to impose this one and this one. The asymptotic condition, sorry. For the asymptotic solution conditions for F and
Daniela,
C, C.
yeah, you say Dirichlet, but they are Neumann boundary conditions for the
Sorry about that. Yeah, because of
for the square. Yeah.
this. Yeah, sorry about that. Yeah, Neumann condition for F and for C, and the asymptotic condition we will write it in as Robin boundary conditions. This one and this one in this way. Sorry. Thank you, Leko. Yeah, everything is okay.
Yeah.
All right. We compact our domain in this way. So it is a square, and we will solve these equations with these boundary conditions. Neumann for F and C, and Robin conditions in the asymptotic boundary, that is in the L line. So the numerical tools, maybe you was learning about that. We will use the Garlickin method to apply finite elements. The central idea is to approximate the solution U as the finite sum of basic functions, where C are the test functions. And the Garlickin method requires to write the residual of a differential equation as orthogonal text functions like this. And we will use the Newton-Raphson method because now we have a non-linear system. Note this is linear for F, but this isn't. Note that we have the unknown function in the denominator. So we have to use Newton method Raphson for solving that part of the system. This method is an interactive scheme for solving nonlinear system of equation of the form like this. Note that we will solve first this one that is linear, so we don't have any problem about that. But for this one, we have to use the Newton-Raphson method. So imagine that equation we have of the form like this, where U is the unknown solution, that is C in our case, and G is the nonlinear residual operation, that is the way that we write the equation. That is nonlinear. So the base idea of the method is to approximate the actual solution using the Jacobian, using the Taylor series, where this is the Jacobian of the functional. So we want to iterate the Newton-Raphson method, like this, we have to use our initial step, and the correction of the unknown function will be contained in this correction. So we update the approximation like this, where J is the Jacobian operator. This is the derivative of G with respect to U. And the step one is to formulate the weak equation. I know that you did that for the case of the Laplacian. So it's the same idea. We use the weak form of the equation. The next step is to compute the Jacobian in this way, where this is the weak equation. The important part is that the Jacobian must be bilinear in both in trains. And the next step is to assemble the linear system. This will do it by Gridap. So we will solving a linear system after all. The last step is to update the solution in this way, having now the correction of for U, until we converge to a solution. So this will be performed by Gridap. So we have to only give the information of the operators. In our case, the equations will be complicated. So I help me with another script. I will show you in a few minutes. First of all, we have to treat start with the treatment of the equation for f. We have the problem has axial symmetry, but the geometry remains 3D. This is important to perform in the spatial weak form. So the weak form for the equation is like this, where this has all the information of the Robin and the Neumann boundary conditions. We have a square, so I will tell you in a minute what means gamma 2, gamma 1, and etc. And after solve the equation for f, we have to start the treatment for equation for c. So the first step in this case, that is nonlinear, is to start the linearization of C, like this way, where C0 is the initial step, and this is the correction. So we linearize the problem in this way. Note that this is the part, the residual, and this is a part of the Jacobian. And the important thing is to linearize not only the equation, we have to do it with the boundary conditions as well. So for the Neumann part, we have this, which lists these two Neumann equation for the C0 and the corrections. And after that, linearize the Robin conditions. In this case, we have two Robin equations, but note that the main part is with the C0. So after that, we have to decompose this the equation of for C. this one, in the residual part with their boundary condition, and the Jacobian part with the boundary condition to C1, the correction. And we do it like this. The residual part, this collapses all the information of the boundary conditions, the Neumann part and the Robin part as well here, and the Jacobian part, and this term collapses all the information of the boundary conditions for the correction. So this is the weak equation for F and the weak formulation for C. Note that in the equation for C, we have the information of the F function, so we can decouple the system. The numerical domain is, you can see the complete domain now, is a square, and these two lines are the gamma 1 and gamma 2, the information of the origin, and in this line we collapse the information of the infinity. The square is of size 1, so this is gamma 3 and gamma 4, the boundary conditions that we impose here. Neumann, and the Robin part for the infinity. So this mesh, I perform it with the HeMesh. I will tell you more about that after the examples. So we have to import the libraries and the mesh that I perform with GMesh. And after that, we define the quadrature rules using the triangulation and the measure of the quadrature formulas. We are solving for polynomials of degree up to 3. After that, we have to tell the triangulation for the boundary. So we have the boundary of 0, 0 rho, and 0 zeta. That will be gamma 1 and gamma 2. And after that, the asymptotic conditions, gamma 3 and gamma 4, with the same degree as our triangulation of the complete square. And note that in the gamma 1 and gamma 2, we have the same boundary conditions. So we make the union for the triangulation like in this triangulation. And after that, we have to define the final elements reference space. In this case, we will do it with this line. In this line, we are defining our space. In this case, we use the Lagrangian elements. So this is the space. And the type of the elements are scalar. In this case, we use float 64, real numbers. We can change these, not in this case, but the library has could perform space, vectorial space, complex space, and also tensorial space. And here we are using second order elements. It's quadratic polynomials in its cells. So here we are defining the basis, the basis polynomials for our elements. And with this space, we have to define the test space. In this case, we have to tell the tell the Gridap the model, the triangulation of the domain, the reference space that we uh, already defined, and the conformity that that we are imposing between the cell elements. So in this case, we are imposing H1, that is continuous functions with square integral derivatives. And we also could define if we have direct tags. In this case, we have a Robin condition and Newman condition that it isn't our case, so we didn't do it now. We won't do it now. And after that, we have to define our trial space. So in this case, it's like this. And after that, I would like to show you I write a script, this one, that contains all the functions that I show you before. It is only for, I don't know.
Daniela, can you change to white background because many things we don't
Okay,
see.
all right. Let me remember how we do it. View. I didn't remember how we do it. Mm-mm-mm. Okay.
Yeah.
Now,
Yes.
better?
Good. Yeah.
All right, sorry about that. Maybe you have to stop me before. All right. I remember that our weak formulation has functions uh, of the coordinates. So I reduce the functions that I need in this script. I will share you the complete file. So I have to include the script that has all the information of the function that I need here. And after that, we start with the numerical solution for f. Sorry for the nota, the the change of notation. U is my unknown function f. So here I am solving the problem for f. Remember that it is a linear solver equation. So we perform a linear solver. We are defining the assemble for the problem here. Remember that B has the information of the terms that has an information of f, or the unknown function. And we have here the Robin boundary condition, and here the Newman boundary condition. After that, we define the solver, in this case linear.
So, Daniela,
Yeah,
this Z is the normal on the Z direction.
yeah. This is here in the auxiliary functions, set a vector.
Okay.
in the structure of vectorial structure that Gridap needs. So here we perform the dot product.
Okay.
Um, yeah, D is also a vector value here. So this script contains all the information of the structure of the weak form of the equation. Maybe you need that explain more about it, Leko?
No, it's okay. I think.
It's a complicated equation, so I prefer to explain the big details. But if it's necessary, uh, I
No,
will explain it,
I think it's, yeah.
right? And after all, we solve the equation for f. I use visit to visualize the solutions, but we can use paraview as well. The it is necessary that I show you the solutions with visit, Oscar. Maybe we can do it, or is unnecessary.
Yeah, you have it in there.
All
That's
right. I write the solutions in this file. So let's visualize it. I will open the folder, sample one, results, and let's visualize the F solutions. It's a scalar one, so I use a pseudo color to visualize it. Visit is big a big software to visualize a lot of things. It's very powerful. Okay, and this is the solution. It's the scale uh, tell us that is a small function, but has the com- comportamiento. I didn't
behavior.
remember the behavior of that we expect. So it's a good one. We can do code like this and visualize the the behavior of the equation in this line. This is a big mesh, remember. Uh, we, after this, find this solution, we refine the mesh to uh, get the the behavior near the origin, but this is a convergent study. I didn't write in the notebook, but we can do it after playing the examples. And after that, we continue with the equation for C. Remember that this equation is nonlinear, so we have to perform the Newton-Raphson method, and that we have to include the behavior of f in the equation. I I do it in this way. Remember that the information of f is contained in this term. So we have to perform the gradient of f to include it in the equation of for C. So we do it like this way. Remember that C is the solution that we we got before. So this is a cell field operations that is in the triangulation. And after that, we define the residual and the Jacobian. An important thing that is that the Jacobian must be linear in the final entrance. And in this case, we have all the information in the residual and all the information in the Jacobian. And we define the final element operator. And remember that we have solved it in an iterative way. So in each step, we are solving a linear problem. So the nonlinear solver must have information to solve a linear equation. We do it in this way. We are defining the linear method to solve in each step. We use it now line searches for that. And here I defining the method. Remember that we use a Newton method, but also Gridap has another background exchange for do it. I tell that I want to see every step, the information in every step, and I define the tolerance for the method and the maximum iteration, and this one I will show you in a minute. But it's a conversion, a stop for the algorithm. So also we have to define a seed. If I in every every time that you solve a non-linear problem with Newton Raphson, we have to define the seed. So now we do it in this way. This is a better seed for us. So it depends on the problem. And after that, I solve it. I tell the algorithm the seed, the solver, and the operation to perform. And maybe this will take a few minutes because I put this way. We will see in every step how wait, it will take time, a few minutes. I hope. So the F information and the step of the two step of the norm, and we can see that the algorithm is well behavior. We have a convergence of the algorithm, so we are happy. And after that, we want to see the solution. We will open the file and we want to see, remember that it's a scalar field, so we can visualize it with pseudo color. And this is our conformal factor, the unknown function. The behavior is expected. And note that in this PDA, the main behavior is concentrated in this zone. So in the mesh, we didn't get the, the main behavior. So maybe if we refine the mesh, we will see the complete behavior for the conformal factor. So we now, for now, we are happy to get this solution. And with this, we finish the example one. I work a lot with nonlinear PDA, so Newton-Raphson is a good friend of mine. It's complicated to linearize some equations, but it's a powerful tool. Any questions about example one? Oscar, maybe I have I
Oh, did you compute the Jacobian for yourself, right?
yeah yeah. Maybe we can use another tools to do it numerically, but I do it by myself. Any questions or comments?
No. We can go to the next.
The next one. The next one. Okay. The next one. Um, in this case, I'm going to show you a little more of what I'm doing in my PhD. We are trying to solve the Einstein equation in stationary formulations. We are taking advantage of the symmetries. So we translate the Einstein equations into a couple nonlinear PDA system for the norm of a vector that contains all the symmetry information and scalar field associated with that vector and a symmetric tensor. Here we like to show you the numerical treatment we did to solve the scalar part of the system, assuming that we know the symmetric tensor, the tensorial part of the system. In this case, we we will again use the Newton-Raphson method to solve it. Note that again we have a nonlinear system of equations, and in this case, this is a case that the unknown function is the equation is R coupled. Um, so we can rewrite this system in this way. And also we have to linearize the system to use the Newton-Raphson method. So the linearized system we can write like this. And express it, x1 has the information of the correction. Remember, it's the same case that we performed in the example one. We have to linearize the system with a seed and a correction in every step. So x1 has information of the correction for the lambda and the omega, where here are the functions that define the residual part of the equation. And also I compact all the information of the functions in this script. You can show it. Example. So I need this script to solve it. The algorithm is the same, but in this case, we have a couple system, so the treatment will be different. We define the mesh. I will show you in a few minutes, but it's a spherical one. We have two spheres concentric. The first sphere of radius 18, and the other one, the big one, is with radius 100. I will show you in a few minutes. I perform the mesh with HeMesh, so I can tell you more about it after the examples. We define the triangulation, and in this case, we have a Dirichlet boundary Dirichlet condition in the two spheres, the internal one and the exterior one. So we have to tell the algorithm this way. In the creation of the test space, we do that because in imposing the Dirichlet conditions, we need to tell the algorithm what will be the value of the solutions. So the test space, we have to be consistent with that. And in this case, we have the exact solution, so we can perform an error, an exact error. And in this case, remember that we have a coupled system, so we will use multi-field space. That is a data structure in Gridap that allows to handle multi-finite element fields together. So we have to first of all create the trial and the test space for each space, and after that we assembling in a combined space that contains all the information for the trial space, the test space, and the trial space. We can also get all the coordinates of the triangulations. Okay, what I have, okay, I defined it before. And this is information of the tensorial space. The tensor that I need to solve the equation. Remember that our initial system has three unknown functions. Two of them are scalar ones that satisfies this equation, and the other one is a tensor field. So to solve this part of the system, we assume that we have this tensor. So I am giving to the algorithm in this way. Tensor value is another type of data that is defined by Gridap. And after all, I perform the test, the residual and the Jacobian part. Remember that now we have two unknown functions that we have to get in a couple, solving in a couple system. So remember that our space now is a file, multi-file space. So we have to perform in this way. This is the step one solution, and or the n iteration, and this is the correction, and this is the linearized part of the system. So Remember that we also had have this like condition, so we didn't perform any uh, integral in the boundary. And in the same way, we have to define the final element operator. And we remember that we are solving a nonlinear equation, so we use a Newton-Raphson again.
Uh, when Daniela, you have
Yeah,
there some expressions like care xi dot gradient of w1 in the
yeah,
Jacobian. What's
yeah.
that?
This perform composition of functions. Here we have I have the care metric here, that is a function. So here I perform the evaluation of the tensor field in all the points of the mesh. Remember that x
Okay.
x are the physical coordinates. So now I have a metric evaluate in all the points of the mesh
Okay.
here. And after that, I perform the matrix product. Remember that this will be a 3D metric, a 3D matrix. So I perform here the matricial product
The
here,
contraction, yeah.
the contraction, exactly. Sorry.
And then you contract
Eh,
the W, the gradient.
exactly. The gradient of the W. So this will be a vector field. So I perform here the contraction of a tensor and a vector field.
Okay.
Um, I have to
And,
explore all the defined function of Gridap to have sure that I am doing here everything that I needed. So in this case, this perform like a contraction in our way. But every time that you have a function that
como una matriz.
you
Háblanos.
W is a or unknown function W of the here.
Okay.
This is W. Remember W and lambda. So in this way, I use the same notation. Lambda is our known function, or W is our omega. This is the test space, and this one is the correction of the step n minus one, the previous step.
And you are
All right.
in Cartesian coordinates.
Yeah, I'm in Cartesian coordinates. Yeah, yeah. Exactly. So now we can continue. Any other question? It's a complicated problem. Yeah, here. I hear you very loud.
So you are calculating care at each metric at each point,
Exactly,
but
exactly.
would you have just calculated it before and then used it there as a matrix, or is it better to use it
Exactly,
that
exactly.
way, or is it better
You
to
can do
use it
it.
that way, precision, something like that? Because maybe,
No. Because this is a matrix, not a function. So I can perform it before, and after that, uh, put information here.
yeah. So my question is if you could just calculate it before and then call it and store it in memory once, and then
Yeah, maybe. This code I made it in 2021, so I learned a lot about
okay.
that before, after that. So yeah, I can perform it before and uh, improve the performance. Yeah.
Yeah, maybe it's the same, maybe it's not. I just was
No,
guessing.
yeah, it could be better because the residual and the Jacobian is calculated everything here. So I
Yeah, but
hago más
it
liviano el
depends because
cálculo.
sometimes calculating something again is better than storing it in memory
Yeah,
because.
yeah,
So
yeah, yeah.
I don't
So,
know.
and remember that this is a iterative
Yeah.
method. So in each step, I perform this. So yeah, will improve the performance to calculate it before and use it here. Yeah,
Okay.
thank you. And also I could calculate it in the script. So yeah, thank you. After that, we use we are cheating the code because it's a complicated system, and I use the exact solution for seed. And okay, it's unnecessary. Remember that okay, I do it before. I had the exact solution, so I could interpolate everywhere in the triangulation. And after that, we will solve it. It will take time. Every time that you had a multi-field function, you have to add this cache. I didn't understand why, but we have to do it. Every time that we perform a multi-field system. So remember that I put show trace true, so we could see every step uh, how the solution are. How is it? All right, and after that we write a BTK file to see the solutions. I perform here also the error, the absolute error with the exact solution. Sample 2, results. We have all the mesh. I will show you a slice, a 3D slice. So here is our lambda solution. And the mesh is something like this. It's a big one. It isn't refined. And we will show you also the twist. The other field W, and also the error. We also can perform here the relative error and maybe the gradient. We can perform a lot of things here in the cell field equations fields that I am writing in the BTK. Remember that this one is a field in the mesh. It's an important thing. And this is all about example 2. Maybe you have a question. This is something similar than the other example. We perform a Newton-Raphson method to solve a nonlinear equation, but in this case we have a coupled system, so we have to perform it in the same time iteration. But the idea is always the same thing. Perform the residual to a step n, and to know what is the correction for the step n plus 1, we have to perform a linear system to know the correction with the Jacobian for this of the system. So the idea is the same that I explained in the example 1, but in this case the form that takes the weak formulation for the system is very complex. Yeah. Yeah. I can share you. I can push it in the PDA repository. Yeah, of course. Maybe writing again the information that I put here of the step by step and the way that we have to perform the calculations to know the Jacobian. Maybe will be clear. Of course, I can share you all the yeah. And here we also had the information of the mesh, not the point here, but I can explain you how to perform it using Gmesh. That is a software to do it. Okay, the example 3 is more fun because we had a simulation. Yeah, break. Yeah, of course. Yeah, of course. How many? All right, all right.
Hi, Daniela.
Hi there.
Hi. We can continue if you want.
All right. All right. Before the example three, something I would like to emphasize when you look at the examples and the notebook is to forget about the physical motivation behind them, especially in the first two examples. Simply try to understand how, given a system, to solve it numerically. Relativity is complex, but the important thing is to use the numerical tools, which are incredibly powerful. Finite elements libraries are capable of performing every complex situation used in multiple and diverse fields. I'm also leaving my contact information in case you have any question after today. Gridap has a very active community where the creators themselves answer questions and where users can resolve issues as well. Here is the community uh, wait, information. I will left you in the chat. Every time that I want to ask something or maybe find information about something, I search messages and maybe issues that other users had before and solve it. So it's a good tool. Uh, and starting with the example three, for the last example, I would like to share with you a project we did for a company in Córdoba. This is the toy model for the project. That given a machine, they were looking to control the temperature in a specific region. Therefore, part of the solution to this was to understand how the temperature evolved within the machine. So we here, so we do it here. I will show you a simplification of the machine in the evolution of the temperature. Unlike the other two examples, this one is linear with a single variable, but the interesting thing is that it's a parabolic equation, so we will have to do it evolution. That is the fun part. And so where our main goal is to solve this equation for the temperature U. Uh, in this domain, I will show you in a few minutes, but it's a box within a small box in the middle that we like to simulate as resistors. Um, so our initial condition is the temperature of the lavatory. Uh, so we will have a temperature distribution in the beginning of the simulation, and the boundary conditions could be three in this case. Dirichlet that specifies a fixed temperature on a part of the boundary. We will impose this Dirichlet boundary condition to assume that the exterior of the box is a fixed temperature. That is a simplified case. And a Newman boundary condition that specifies the heat flux across the resistor boundary. That is a box in the big box. I will show you the mesh in a few minutes, where this is the heat flux. In this case is a positive one, so it means that the flux is entering in the domain. And other condition that we impose after this toy model is the Robin boundary conditions that this models a convection between a body and the surrounding medium, like air. In this case, it would means that the body is losing energy by convection between it and the medium. So this is the weak formulation. Remember that we have a parabolic equation, so we have to treat it in another way. So the first step is to perform the weak formulation, where B will be the space of the solutions. The first term accounts will be important for the transient behavior of the equation. It's our time-dependent part. The second terms represent the diffusion, the heat conduction, and the right-hand term include the internal heat sources. In this case, will be zero. So we are representing the resistance in the Neumann condition. So we don't have any heat sources here. And the full algorithm is a transient FEM. I think that Gridap has in their tutorials one transient equation. And well, here alpha is the thermal diffusive that change with the material. But here we will suppose that the thermal diffusivity is constant in all the box. And yeah, the heat source will be zero. And we perform the simulation in the physical domain, the spatial domain, omega, that will be our box, and domain, time domain, that will be represented in this way, where t is the final time. And the algorithm structure to solve it is we discretize time using an implicit background change that is handled by Gridap. In particular, we provide the fuel time weak formulation directly to Gridap's transient FEMS operator. The strong form of the equation, remember that is this, with a non-Newman condition, the boundary, the internal boundary. And Gridap handles time discretization implicitly by the requiring the user to define the residual function, that is the fuel weak form of the PDA. It includes both the time derivative, the diffusion term, and the boundary sources. The spatial Jacobian, that is the usual Jacobian, but excluding the time derivative term, and a time Jacobian, that is the derivative of the residual with the time derivative of u, that will correspond to the mass term. So the variation form provided to Gridap is this, where this will be only one integral in the internal boundary. And after that, we will perform the spatial discretization that we explained before in the same way, using final elements and everything like that. And the important thing is to discretize the discrete system at each time step. We have internally solved the nonlinear system, this one, where M is the mass, the mass metric assembled in this way. That will be our time Jacobian. K is the stiffness metric, that will have all the information with the spatial Jacobian. And after that, the global term of the boundary, the Newman boundary sources. So Gridap assemble and find the solution. Only we have to define this matrix. So we import all the libraries. In this case, we use, well, maybe I will show you the domain after that, but it's a box that includes a box inside that is the boxes are two concentric boxes. The internal one represents the resistors, and the big one represents the machine. So I add the mesh in the folder. We perform the triangulations. So in this toy model, we use Dirichlet boundary conditions in the exterior of the domain, and a Neumann condition in the internal boundary that we imposed to the model the injection of thermal flux into the system by the resistors. So we had only one Dirichlet tag, the exterior one, and we have to perform the boundary triangulations for the interior, the internal boundary. Here we had a decomposition of the boundary, because in each phases of the box, the flux will be different because the direction of the flux will change. So we have to perform an integral in each phase of the box. And here we have the information of the initial data that will be the temperature of the laboratory in Kelvin degrees. So this is our test space. And here we define all the constants, not only for the diffusivity term, and also for the flux term for the resistors, the Neumann boundary conditions. Everything in this example is constant. These numbers depends on the material. And after that, we have to define the residual and the Jacobian. Remember that this will be the weak formulation of the complete equation, containing information of the sources. The Jacobian part that is performing the problem like before, and the time Jacobian that has the part of the time derivative of the solution. And after that, we assemble all the operators. We will use as linear solver to the space part. And after that, we start with the time configuration for the problem. We will solve from 0 time to 10 time using steps with this. we will use a theta method. Gridap has a lot of time solvers. Theta method is one of them. After that, we solve the problem, interpolating first of all the temperature everywhere. We solve the other part, and here in up we had the information of the Jacobian and the residual parts. So the simulations was performing so fast, and here we write PVD to visualize the simulation that consists in a lot of BTU for each time step. So this will take time. We are writing a BTU for each time step, so will take time. So now we can, this PVD has all the information of each BTU, so we can show, we can see, let me remember, like this. This is the domain. It's a box with a little box inside that represents the resistors. So in the exterior boundary of the domain, we impose Dirichlet condition, and inside we impose Neumann conditions to simulate the flux of the resistors. And we can see the temperature evolution. After that, we improve not only the boundary conditions, as well as we improve the Dirichlet, the diffusivity terms inside the machine, because the machine had different parts made of different materials. And we improve the Neumann flux of the resistors. So this is our toll model. So after that, we finished with the example 3. Maybe you have questions. I hear you very low, Oscar. Hello?
No, just comment.
Ah, okay. This was the very first time that I performed a parabolic equation in using Gridap, so it was very fun for me. You can do very fun simulations using this tool. So any questions? Or maybe I can show you how I made the meshes.
Yes, we can look at the meshes now.
Okay. I perform the meshes using Gmesh, the software of Gmesh. You can download the source code in here. I will share you this one. I didn't use the library because I had a lot of issues using that. So I perform the mesh using the software, and after that I import the meshes using Gridap. So this is the software, and I start with the elementary entities like points, lines, circles. In you can see, or maybe I oh, I can do zoom, but I don't know. Okay,
Is it okay? I
are you
think we can see
okay?
it. Okay. Yes.
Okay. Yeah, you can add parameters, point lines, uh, circles, ellipse, rectangle, disc, spheres, cylinder. I prefer to perform each entities by hand. It means like if I want to do a disc, I perform the points and after that the arc, the circle arc, because maybe sometimes these entities, the disc or the cylinder, um, forget a point. In some case, the circle forgets the initial point of the circle. That means if I want to do a circle, I have to set the center of the circle in 3D, the radius, and after that I add it in this way. And sometimes Gmesh forget the initial point, so I find that some code had a big error around it. So I prefer to perform the points and after that the circle arc. Uh, we can edit the script. That is a geo script that I think that you are made it by hand in a script of Julia. That is the same the same structure. I can perform, I will, we will forget about it. Change the script will change our visualization. And I would like to perform a box with an interior box that will extricate. I don't know the verb, but we will try start adding points like this. Will I will perform only a square in a XE plane. So I will start. Okay, what happened? Okay, what happened? Okay, then, okay. I will. Sorry about it. I will delete this thing. I will start again. I will like to generate a mesh that is a square with a square inside that will extricate, and we will do it by hand to explore all the things. We will start adding points like this. That is our stain initial point, and I would like to create a parameter that will be L, the size of the box. We will start a value with 1, and maybe I want a rectangle, so I will change that size for X and for Y. So after that, I would like to start creating the other points. Point LX 0, Ly the other point, and all right, after that I press Q, and we start with the lines, creating the lines that will be our boundary. And after that I create the inter box.
How do you create the line? You press some
I
controls or
press
something?
only line. Sorry, I will do it again. Remove the last script. Okay, I will start again. I press line, add a line,
Yeah.
and after that, line. After that, I select the start point and the final point. So that creates me a line.
Okay.
If I want to create a circle arc, I have to, maybe I will do it again. I have to also uh, enter a radius. I will perform a this after the box, so I will explain it before after. So I have to perform all the lines of the square like this. Notice that when I press a start point, the software tell me that I have to select the end point. So if I press the same point, there will be appear an error. And after that, having all the lines, I press Q to finish the creation of lines. And after that, I will start with the interior, the internal square, maybe of the size, the half size. Add, and the other one. This is we are creating the parameters. The um, the advantage of has parameter is like if I want to change my size, I only have to change the parameters here or here. So it will it's better than change the numbers inside. This is the same structure that you made before in the other classes, creating the point geo. So we will start with the points. And remember that if I want to create a concentric square here, maybe I will do it. We will do it in a center here of the big square. So the first point will be in LX, will be here. Sorry. That will create me a point here. Oh, sorry. You can see the red point now. No? No?
Yes. Now it
Yeah, because if I move the mouse, the point will change. And here, alignment. I have to add it.
okay.
This is the point that I add now, and I will continue with the other points. LX. Oh. Here, if I want to do it by editing the script, I can do it. Will be faster. Oh. I only have to change the number of the points and the where I add in the points. So reload the script. I lost a point. Here I have an error. Here I have an error. Sorry. Here also. This is the point. No, this is the same point. Sorry. And I have to add. All right. I think that is okay now. So yeah. And after that, I start creating the lines in the same way that I did it before. And after that, I have to tell to the software that this will be a plain surface in this way. Create this surface and the big one surface. That will change our script in this way. That create a curved loop. And after that, a plane surface. This is a 2D entity. And after that, I want to extirpate this area. So we had a Boolean operators. For that, I will change the center of the small square to show you better the better. Let me do this to show you better the okay. I will perform a difference a Boolean operator that will extirpate an entity. I have to indicate that what entity will be. In this case, we use surface. And after that, I have to start selecting the big one, the big 2D area that these are the big square. And after that, I have to press E, and I have to select the area after that I want to extirpate. Oh, sorry. dimension. Okay, what's the problem? Sorry. Okay, maybe I change the order. Maybe I have to press here the area that I want to extricate. No. This happens me all the time. Sorry about it. I don't know what is this. Look at the script. No. Okay, I have to do it in the other way. Difference, surface, selects the big area and that area, and after that I don't know why what this appears. Okay, this happens to me all the time.
I
Maybe
think I think for the Boolean you need the open cascade.
I had the open cascade at the beginning. Oh, I didn't have it. Okay, yeah, I have. Sorry. I have to have this at the beginning of the script. Thank you about it. That's it. That is. Yeah, I forgot the open cascade at the beginning of the script. So the Boolean difference, we have to set the bigger area, and after that, the small area that I want to extricate. Thank you, Oscar. And after that, we can see the mesh, if the mesh is the thing that I want to do. We also can set the refinement points. In this case, we had the points has the refinements 1, but we can change this. Maybe we can change the origin point. Ask a refinement like this. This parameter change, this is the x, y, and zeta, where are the points, and the 4 parameter are the refinement parameter of the point. So if I change it,
Can you put the thing in white also because we don't see the red?
yeah. Okay. We will point a refinement like this.
We don't see what you put.
0.05,
Okay.
and in the origin I point 0 extra, 0.005. Remember that is a box of size 1. So okay, I use the same refinement for all the points except for the origin point that is finer. And we have to reload the script, and we can see the 2D. See that the origin refinement is better, but if I want to refine the mesh, I only have to put here refine by splitting, and this will be a smaller mesh. So I move the interior square, only to select the boolean. If I want to have it in the center of the big one, I only have to edit the script, move in the center of the smaller square. And after that, I have the square. If I want to give information about the boundary, because I want to impose the Neumann condition or Robin condition, I have to set the physical groups. I have to add the surface. That will be the interior of the domain. And the curves like this. The exterior region will be this and this. I can change the name. Maybe if I want, like in the first example, that I want to give the origin, origin boundary, and after that the exterior boundary, I can do it in this way, changing the name x0, like I want to difference the physical groups. I can do it this, and I had a different name for the boundary. And maybe I want to give the interior boundary like this, all the boundary together. So that names will be the names that I have to put in the Gridap boundary triangulations here. If I want to put int, or maybe I want to have the triangulation of the boundary, then the tag, that is the tag that I put in the physical groups. So in this way, we have this mesh. I want to change the name, and before that, I want to export the mesh, because this will, all that we made is to change the point geo. But if we want to export the mesh, we have maybe this mesh. We have to save mesh, and that will export me this point mesh. Maybe we can change the name.
So there, Daniela, you're having like a very high resolution near to the origin, right? So
Yeah,
what about
because
if you wanted to change it to have better resolution near the interior square or
you
something like that?
okay, you have to only change the parameter of the resolution, that is the last number of
Okay.
the points. Maybe you can you want to change the resolution in the exterior, and you have to change only here the put a smaller number. I'm putting maybe a smaller resolution than the origin point. I put in the origin point 0.005, and now I put it in the exterior point 0.001.
Okay.
So in that case, reload the script, see what happened.
Okay.
Now, so changing the resolution of each point, you can refine the mesh around the point. But if you want to have all the points in the same resolution, and only you want to refine all the mesh, you can do it refine here, pressing refine by splitting.
Yeah, but
And
if I
it,
want to refine an entire line, an entire boundary,
okay, you maybe we can refine the all this line, the y0 line, we have to put to the other point, this one, the same resolution than the origin point.
And that's enough, just to...
That's enough.
Okay.
Let's see. The other point was this one, so I put the same resolution than the origin point, and that will reload script and the refinement. So maybe I can change the exterior point to the same resolution after all to see the effect. So that will change to the same resolution to all the points here.
And if it was like a circle, you just put also one point and it just propagates to
Exactly. Now we will do a circle because the algorithm to make a circle arc is different than the square. Maybe we can save this and start again. Okay, that. I will share you this script after all. Start again. Maybe we want to make a circle. We of course can use the disk entity that made us we perform a circle, we radio once. Okay. Oh, it is an elliptic one. Okay. Sorry. I want a circle, sorry. 0, 0, 0, 1. Add. But in this case, the mesh, I don't know why, but forget this point. So if I want the same circle, I have maybe add this point to the circle, but we can do it by hand, make the circle by hand. So we don't have to use this entity. Why? What we do this? We have to put the center of the circle like as a point. After that, start to add the 4 points of the circumference. So we have to add a point, the center of the circle, and after that, the point. Maybe we want to do this by adding. Adding a parameter that will be the radius of the circle. We will set by 1. After that, we will start to put in the other points. Add the point 0R, the point that's a quarter of the circle, the point minus R, and the last one, the point minus R 0. Okay. And after that, I have to start with a circle arc. I have to perform the start point, the center point, and the end point. And that will create a circle arc, right? Is a different method of the line. So, okay. I forgot the center point. And the other quarter. And I put 2 points. I made a mistake here because all right, and after that we have to make a plane surface, choosing the boundary, and maybe I would like to change the refinements over a point. So only the thing that I have to change is this number. Maybe I would put here 1.505, and the other points will have the refinement 0, 0. Okay, this is the center point, so won't be important. I would like to change the refinement over this point, so I put a smaller parameter than the others. And after that, I will create a mesh. It would look like this. Reload. Okay. Notice that in the point over here, the refinement is higher. Maybe we can put a bigger parameter in the others to see it clear. Like this. If I refine the splitting, this point will be refined finer than the others. And if I want to create a physical group that will be the exterior of the circle, I have to do it like this. Curve and press a name, X, all the lines. And I can save the mesh like this, and that's all. Yeah,
This is going to have the points at the extremes, right?
exactly, because I am adding the points explicitly. But if I want to maybe, okay, reload the script. Maybe I want to create a bigger circle, and I don't want to do it point by points. So I want to do it like this. Maybe the center of the circle will be, and the radius will be maybe 2. Add. So I have this circle, and I maybe, plane surface, create the bigger one, and maybe I want to perform the Boolean operator to accept the smaller one, difference, entities, surface. I have to import the bigger area first and the smaller area after all. Notice that the little line that we had before, it doesn't appear now because I performed the Boolean operation successfully. And now I want to put this point in the mesh. So only I have to make a point, select this point. I put it. Let me notice that I put the point. No. Point. That will be the point 2.00. Add. No. Okay. No. 0.2. Add. Okay. the script, I will delete this point, and I have to, when I made the physical groups, I have to add now the total area, and after all I have to add this point to the physical groups. Point that I want to add, I have to mark this point with a physical point group. Point, and the exterior curl, exterior, and after that, when I want to make boundary triangulation, I have to put like this. If I want to make a triangulation of the exterior of the circle, I want to add where are here boundary, the exterior and the point. And in this way, this gamma will have the information of the triangulation of all the exterior boundary and the point. All right?
Okay, yeah.
In this case, I solved the problem of the forgotten point here like this, instead of made the circle by hand. So one way or another. So this is my mesh. Remember that we had a refinement point here, so the mesh will be refined over there. And that's all. If I want to refine the circle, notice that the circle by hand, I have to refine each point. But if I want to refine all the circle that I made in this entity, I have to perform something like this here. I think that. Okay, no, maybe no, that it isn't that entity. Sorry. So maybe if I want to refine the complete circle, I have to refine this point over there. But that's why I perform the circle by hand, because I have control. I have control of the refinement of each point. So I prefer do it by hand instead of the circle entity. So that's all.
Okay, thank you, Daniela. Questions?
This is a very powerful tool. I didn't try to make a plane, but here you have a lot of tutorials that help a lot. Some companies made the point geo in design software, and after that you can import in Gmesh and make the mesh by hand. So it's a very powerful tool. Now we perform 2D meshes, but you can do it the same thing in 3D.
You can use this extrude, right, to make a 3D out of it.
Stroke. I didn't know the words.
This is a after above Boolean.
Yeah.
You have the extrude.
You can exactly. You can perform these operators in a 3D as well.
Yeah, that the extrude, I think it creates out of this grid, it creates a 3D grid,
Okay. Okay.
I think.
Every time that I want to perform a 3D entity, you only have to change. You remember that the points had a 3D representation, so now we set the zeta coordinate to 0, but you can change it. And also here you have 3D entities like a sphere, cylinder, box, torus, cone, etc. And you can perform the volume in the same way that we perform the plane surface. So if you want to add all the points and after that create a volume, the performance will be the same. Create the point, create the lines, and after that create the volume.
Okay. I think
All the secrets, yeah.
with the extrude you can do, say, you take this cylinder you have there and create this disc and create directly a cylinder. There is,
Okay, maybe translating the
I don't
circle.
remember how it is, but
Okay,
once I did it, can do a sort of automatic cylinders goes up.
okay. Yeah, also you have the transforms things. So if you perform like this, you can translate it, rotate it, made it symmetry.
I think
It's
the
a
one
very powerful tool.
maybe the one that says pipe, the extrude. I don't remember how, but
Maybe I didn't use it extrude, but
remember
maybe curves. No,
all entity.
all entities. Mm, okay, volumes. Maybe no. Maybe it isn't. I can use it now for the structure of the mesh. I don't know. I didn't use it
Okay.
before, but it's a very powerful tool, and the documentation is very well. I think that over here you have the tutorials, and it's a here. That's it. This explain all the information to build a lot of mesh, and it's a very one made the geos, the GMS options, and all the details. And maybe if you want to, I don't know, create a sphere with this or that, there are a lot of tutorials on YouTube. So it's a powerful tool. I prefer to use the software to visualize the mesh that I am creating, and after that export the point mesh and with app import the mesh like we did it before, like this. But it's the same thing. The point geo has the same structure that I think that you are using before. So
Yeah, I think this is the best way to proceed.
I prefer this way because I can see it, and if I am making a mistake, I can see it over here and go to the line that is a problematic one and something like that. But it's so light the software, so I prefer it. But it's the same structure that you are doing before.
Okay, thank you, Daniela. If,
Right.
okay, if you want
I will
to
share
pass,
the
the
folder, the
examples.
complete folder, the
Okay.
examples, and also the meshes. If you want to explore the point geo or something
Yeah,
like
yeah, yeah.
that, I will share you the complete folder. And the folder has also the point mesh and the script with the auxiliary function, so you can play with the notebooks. And if you want help, I will be able to give you my contact.
Okay.
All
Thank you.
right, thank you all of you, and we'll be in touch.
Okay.
Bye bye, everyone.
Bye, Daniela.